Suppose now we have x equals a plus bt squared, y equals c plus dt squared, and we're going to put units in these things in a minute, with the condition that a of 0 is 4 meters per second squared times I plus 3 meters per second squared times j. Okay, I'm going to write the r of t vector. Very simple. It's the x vector times the I, the x component times the I vector, the y component times the j vector. I want to put units in these things. Remember that the x and the y have to end up with units of length. We're going to do this in the SI system. We're going to assume SI units so that length is in meters and time is in seconds. So what do the units of A have to be in order to give us units of meters? Well, A has to be in meters, doesn't it? So we're going to say A meters. What does B have to be? What do the units of B have to be in order that BT squared have units of length? Well, BT squared is going to have units of meters. T squared has units of seconds, so B had better have units of meters over seconds squared, so that when multiplied by T squared, which is going to be in seconds squared, you get meters again. So we get units of meters. So you should pause now and just think what the units of C and D should be, because we're going to put those units on the expression for the J component. You should think that through yourself before you watch me do it. Okay, I'm doing it now. C, of course, has to be in meters, and D has to be in meters over seconds cubed, so that when multiplied by the cube of T, we get meters. So these are the units. Okay, so now what do we know? We know that our velocity is just the derivative of that, and that's going to be, the A meters and the C meters are both going to have derivative 0. And the B T squared is going to, well, the T squared is going to have units, is going to be 2T. The T cubed is, the derivative of T squared is going to be 2T. The derivative of T cubed is going to be 3T squared. And we're going to get B meters per second squared times 2T. I'll put the 2 out here in front of the B. And here's the expression for the I component. Does that make sense in terms of the units? Meters over second squared times T. T is going to be in seconds, so meters over second squared times seconds is going to give us meters over seconds. And that is the unit we expect for velocity. And then we have here plus 3D meters over seconds cubed times T squared J. And again, if you multiply the second squared you get from squaring the time by the meters over second cubed, you get meters over seconds, so that the velocity vector comes out with units of meters per second. And then the acceleration vector. Derivatives are going to be very straightforward. The derivative t is 1, so we get 2b meters over second squared times I. And we're going to get a 2t here. That's going to give us 6d meters over second squared times j. And we got a t in there. Unfortunately, I have to kind of jam it in there, but you should be able to see that. Okay, there's our acceleration function. And of course, that has to equal, well, our acceleration function at 0 has to equal something that it can't equal. I'm going to have to pause here and take a look. I might have made the wrong notes about the function. See if you can see. Of course, it's going to seem like I'm going for just a second. I won't be going long. See if you can figure out what I'm pausing at here. Why am I going to run into trouble setting a of 0 equal to this expression? Okay, all I'm working from here is a very sketchy outline of each problem. And the problem said that the acceleration 1 second after launch, this is a rocket problem, that the acceleration at 1 second is equal to this. So acceleration, and since that's at 1 second. So acceleration at 1 second is 4 meters per second squared times I. And I'm a step ahead of myself. I need to be substituting the okay. A at 1 second is going to be what we get when we substitute 1 second in for t in this expression, and it is going to be equal to this. So we're going to set the two equal, but I want to start by substituting the t equals 1 second into this expression. Well, we get 2b meters per second squared times I plus 6d, and when I wrote this down I was careless. It's meters per second cubed times t for reasons that I articulated earlier. It's meters per second cubed times 1 second, and that's times j. So that equals 2b meters over second squared times I plus 6d meters over second squared times j. Because when we multiply the second by the reciprocal second cubed, we get the reciprocal second squared. And that should equal the 4 meter per second squared times I plus 3 meter per second squared times j. And let's see if I can get that in down here and make it legible. So that's 4 meters per second squared times I plus 3 meters per second squared times j. And now we can directly compare. The 2b meters per second squared has to equal 4 meters per second squared, so that 2b has to equal 4. And the 6d meters per second squared has to equal 3 meters per second squared, so 6d has to equal 3. b equals 2, d equals 1/2. And now we can write our x and y functions, or our t vector. Let's just write it that way. Our r of t vector then is a, which is we got more conditions. Okay, we have another condition that I didn't write down. The r of 0 in this particular problem is going to be 0I plus 50 meters times j. And this corresponds to a rocket fired from a tower 50 meters tall. We're free to choose the x-coordinate of the position, or we're free to choose the origin as far as that goes. If the origin's at the bottom of the tower, then we have 0I plus 50 meters times j is the position at the top of the tower. And from that, we determine, and I'll let you work out the details of that, but that A has to equal 0 and that C has to equal 50. So now we can write our r of t function, which is 2 meters per second squared times t squared I plus C, which is 50 meters, plus D, which is 1/2, and that's meters per second cubed times t cubed times j. Now, there are questions that are asked about this this motion, and we'll talk about them in a second. Okay, any other questions that are posed on this particular problem can be answered easily in terms of the velocity and acceleration functions. The velocity function we see here, the acceleration function we see here. We plug in our values of b and d, so we get velocity as a function of t equals 2b, b being equal to 2, so that's going to be 4 meters per second squared times t times I, and the j component, 3d, d being 1/2, so that's going to be 3/2 meters per second cubed times t times j, and our acceleration function is just going to be 4 meters per second squared times I. Almost wrote t there. I did write t there. You can see I erased it. And the 6d is going to be, well, double the 3/2. It's going to be plus 3. The t here is squared. We would be getting rid of the half if that wasn't squared. You can think about why. Meters per second cubed times t times j. Now, any question asked about the velocity or the acceleration or the position can be answered in terms of these functions.